Hey everyone, welcome back to the Science and Mathematics Clinic. In this tutorial video, we will look at circuits with more than one battery. In our example, we have two batteries, the 45 volts battery and the 18 volts battery. This one here is the 18 volts battery and this one here is the 45 volts battery. Then we have a 0.5 resistor, the 6 ohms resistor and the 0.5 resistor there, and another 1.5 resistor in this circuit. We also have the 2.5 resistor there. Then we have the direction of the currents given as I2, I3 and I1 here. So how do we solve problems like this one? Well, to solve problems like this one, we apply Kirchhoff's laws. We apply Kirchhoff's circuit laws. So the first Kirchhoff's circuit law states that the first Kirchhoff's circuit law is the Kirchhoff's current law, KCL. It states that the total current entering a junction equals the total current leaving the junction. So you have to identify a junction. So here we have a junction. So the total current, like this one here, it's the only one entering the junction, must be equal to the two currents that are leaving the junction. And then the other one is Kirchhoff's voltage law, which states that the sum of all electrical potential differences of voltages around n closed loop is 0. So you have to identify n closed loop in your circuit, and then you have to equate all the voltages or the potential differences across the resistors and also the EMFs of the batteries to 0. So what are the ints? What are the ints that you have to use when solving or when applying Kirchhoff's circuit laws? 1. Identify all the junctions in the circuit. And then you have to write an equation for each junction where the sum of currents entered in the junction is set equal to the sum of the currents leaving the junction. Then secondly, you have to identify all independent loops in the circuit, and then you have to choose a direction for each current arbitrarily. So you can ignore the direction of the currents that are given in the question and then you just choose yours. What will happen is that if you calculate for the current, then you find that the answer is negative, then it means that the current flows in the opposite direction to the direction that you chose. Then, thirdly, you have to choose a direction to traverse each loop. Okay, so you can choose the clockwise direction or the anti-clockwise direction. Then for each loop, you have to write an equation where the sum of all the voltages, gains and drops is set to 0. Then the other thing is that when moving through a resistor in the direction of the current, the potential drop is negative. Then when moving against the current, the potential rise is positive. Then for battery EMFs, if you move from negative to positive terminal, there is a rise in potential, so that will be plus E or just positive potential. And then if you move from positive to negative, then there will be potential drop. This is because the positive terminal is at high potential, then the negative terminal is at a lower potential. After that, you will have a system of linear equations which you have to solve simultaneously. Now let us look at an example. Let us solve the same question that we have, applying this that I've just mentioned there. So we choose the direction of the currents. We choose the direction of the currents and the loops arbitrarily. So what I will do is I will ignore the direction of the currents that are given in the question and I'll just choose mine. Okay, which implies that even you can ignore the currents that are given in the question and then you just choose yours. Then you also choose the loops, the direction of the loops. like this here. So this is the same question. So I've ignored the direction of the currents. As you can see, I've reversed this current. Okay, then this one is pointing up, and then that one I've kept it the way it is in the I've kept it the way it is in the question. So you can see that this direction that I've chosen are different from the directions given in the question. Then I've chosen the clockwise direction for all the two loops that I've identified. So there is this closed loop here. Okay, if I start from the battery here, I can move from that battery to 0.5 to 6, then to 2.5, then back to the battery. So that loop is closed. It is complete. Even if I remove this other loop here, that circuit will still remain. So there is also another loop here. This one is also closed loop. So I've also given it a clockwise direction. Then I have to apply now the Kirchhoff's laws. So first I apply the Kirchhoff's current law, which states that the sum of the currents entering the junction must be equal to the sum of the currents leaving the junction. So in our question, okay, in this case, and depending on the direction that I've chosen, there is one current here which is going into the junction. You can see I3, okay, the arrow is pointing up into the junction there. So then there are two currents. This one here is moving away from the junction. Same applies to I2. So I3 is equal to I1 plus I2. Then secondly, that I name that equation 1. Then secondly, I write the equations for each loop. So by applying Kirchhoff's voltage law, okay. Then for loop 1, what will be the Kirchhoff's voltage law? Okay. So I will start my movement from the battery here. So my starting point here is the 18 volts battery in this case. Now I'm moving through the battery from negative to positive, so that will give me positive 18. Then minus, okay, I'm moving through the resistor in the direction of the current, so this will give me a negative potential. Okay, in the negative potential, it will give me the negative potential difference. So this, and how do I calculate that potential difference? I multiply the resistor given and the current. So the current here is I2. You can see that even this current here is I2. This current here is also I2. So I multiply that with 0.5, then plus 6. I'm here now. Okay, I move, then I'm at this point. I'm opposing the current. Okay, I'm opposing the current I1. So this will give me a potentialize. Okay, so that will be 6 times I1. Then after that, I'm at this point here. I'm moving in the direction of the current, so that will give me a potential drop. And how do I get that potential? By multiplying the resistor times the current, and the current is I2, so that will give me negative 2.5 I2. This should be equal to 0. Then secondly, for the other loop, loop 2, this one here, okay, I will also start from the battery, the 45 volts battery. Now according to the loop that I've chosen, that is the clockwise direction, so I'll move from positive to negative. That will give me negative 45, because I'm moving from high potential to lower potential. That will be negative 45. Then I continue the movement. Now I'm at this point, the 6 volts and the 6 ohms resistor. Okay, now I'm moving through this resistor here. I'm moving through this resistor here in the direction of current 1. So there will be a potential drop here given by 6 times I1. This will give me negative potential drop, and that's it there. And then I continue with the movement. I'm at this point here. I'm also moving in the direction of current 3. You can see that this is current 3. This is current 3 here. So this will also give me a negative potential difference given by the resistor multiplied by the current. Okay, so that is 1.5 times I3. This is it here. I continue with the movement. Now I'm at 0.5 ohms, and I'm also moving in the direction of current 3. So since I'm moving in the direction of current 3, this will also give me a negative potential difference given by 0.5 times the current through that resistor, which is I3. I also set this equal to 0. Okay, so now I have 3 linear equations. Okay, equation 1, equation 2, and equation 3. Okay, so we have to solve these equations simultaneously. Okay, we solve these equations simultaneously for current 1, current 2, and current 3. You can see that these are the only 3 variables in our equations in our equations there. We can start with equation 3. You can pick any equation, then you can use any method that you know to solve this system of equations. Okay, so I'm going to use substitution and elimination in this case. Okay, so I'll start with equation 3. So I reduce equation 3. You can see that this here and that there can add. Okay, so we add this. Since they are having the same sign, this will give us negative 2i3. So the equation reduces to negative 45 minus 6i1 minus 2i3 is equal to 0. Now I can substitute this into equation 1, and let us look at equation 1. So this is our equation 1 here. This is our equation 1 here. We can substitute for I3 there. We can substitute for I3 there. Or I can substitute equation 1 into equation 3. It's the same. So since in equation 1 I3 is already the subject, so I pick this equation here, and then where there is I3 is equal to I1 plus I2. So I get this and substitute it there. Okay, you can see that this is what I've done here. Then I distribute the negative 2. So I just copy negative 45 minus 6i1, then I distribute this, will give me negative 2 times i1, that will be negative 2i1, then negative 2 times i2, that will be negative i2. This gives me 0. I can label this as equation 4. Okay, I can label this as equation 4. Now I can use this equation 4 and equation 2. You can see that now in our new equation here, there is I1 and I2 as the only variable. And then if you check our second equation here, this one here, there is only I2 and I1 as the variables. So you can also add 0.5 and 2.5 to get negative 0.3, because this is I2 and this is I2. So the two terms can add. Okay, so that will give us, if we add 2.5 and that will get negative 3i2, then we just copy 6i1, which is there. Then this 18 can go to the other side and its sign changes to positive. Okay, then I also copy equation 2, equation 4, our new formed equation there, which is this. I also copy it and drop it here. Then using elimination method, I solve this system of equations where I exchange. First, I want to eliminate 2 here, so I can take that 2 here, I multiply it with what is on top, and then I get this 3 here, and I multiply it with what is there. Then the goal here is to get the same thing here, since I want to eliminate I2. So if I multiply 2 times 6, that will give times 3, that will give me 6. Then 3 times 2, that will also give me 6. So I can add that and eliminate 2. Okay, so if we now multiply this times that, we'll get negative 6. Then 2 times 6, I'll get plus 12. Then 2 times negative 18, that will give me negative 36. Then similarly, I get the O negative 3 here, so that I get the positive here, so that when I add this, will just give me 0. So negative 3 times negative 2, that will give me 6i1. Then negative 3 times negative 8, that will give me 24. Then negative 3 times 45, that will give me negative 135. Now if I add these two new equations here, if I add them, this will give me negative 6 plus 6, that will give me 0. It is eliminated, and that is the reason why this is called elimination method. Then plus 12 plus 24, that will give me 36 I1. Okay, that will give us, so this is 12 I1 plus 24 I1. This will give us 36 I1. Then minus 36 plus minus. Plus minus, that will be minus. So this is minus 36 minus 135. This will give me 171. Okay, now I can divide 36 throughout. So if I do that, okay, you can pause the video and then you see what you will get. So I'm getting negative 4.75 amps. Don't forget to include the units there. And you can see that now the answer is negative. Now remember what we discussed in the introduction there. Okay, I said if the answer for the current is negative, then it implies the direction of the current is opposite to the direction which you chose. Okay, then after that, we can get this now and substitute it in one of these equations that we use to solve for I1. So we can substitute it into I4, into equation 4 or equation 2. Okay, so if we use equation 4, then substitute for I1, what is it that we will have? So we have negative 8. So here, that's where we are putting our value for I1, which is negative 4.75. Okay, so you substitute there, then you just copy minus 2 plus I2 equal to 45. Then you distribute this. So negative times negative, that will give you positive. Then 8 times 4.75, that is giving us 38, minus 2I2, which is this one here, you just drop it there, is equal to 45. Now we can solve for I2. Solving for I2, we can take this 38 to the other side. By the way, this is negative 45. This is negative 45. Okay, so you can, okay, so what I've done here to get negative 45 is that this variable here, I've taken it to the other side so that it becomes positive. Then this one here, I've taken it to the other side so that it becomes negative. That's where the negative 45 is coming from. Then I maintain this to be positive 38. Okay, then after you compute here, then you divide by 2, you get negative 3.5 as the value for I2. Now we can substitute these values into the first equation to solve for I3. And we know from equation 1 that I3 is equals to I1 plus I2. So let us substitute for I2 for I1, which is negative 4.75, and I2, which is negative 3.5. That is giving us negative 8.5. If we add, negative 8.5, yes, that is correct. Now you've seen that all the currents here are giving us the negative values, which implies that the direction of the currents that I chose to get these values is opposite to the real direction of the currents. You can see that from the question I changed the direction. I just created my own loops, and I chose the new directions, okay, different from the directions given in the question, okay. So which implies that the values just for I2, I1 and I3 are just I1 4.75, then I2 3.5 and I3 8.5. Not 8.5 but 2.5. Sorry, this should be 2.5 instead of just 5. This is 2.5. Yes, so this is 2.5. These are the values of the current. Please, if you like the video, leave me a comment, like the video, subscribe to my channel, and invite others to also subscribe to my channel to support this work. Thank you. See you next time.